first one at least. So our first invited speaker will be Professor Mathieu Javaux from IBG3 in Juelich and Université Catholique de Louvain. And he was celebrating his birthday yesterday, so hopefully he didn't have a hard time and he will give us a really good lecture. Thank you, Mathieu.
Thank you, Felicia. Okay, so I'd like first to thank the organizers for inviting me. And yes, I know this title is a bit provocative. It's Does Root Architecture Matter in the Quest of Mortal and Plants to Water Stress? What I'd like to convince you through this talk is that modeling can be helpful to understand the role of architecture versus hydraulics and to understand how plants take up water and how they can deal with drought conditions. Yeah, I will disappoint you because I won't speak about hydrotropism. It's a session on hydrotropism, but it's not a talk about hydrotropism. It's a talk about modeling and how modeling can help understanding soil-plant relations. So as you know, water is a constraint on plant growth and food production worldwide. So it's one of the biggest abiotic stress. And roots are good candidates to improve plant adaptation to drought. However, the interplay between architecture and root hydraulic properties is not really clear. You know, probably all of you, that the water flow in the soil plant systems move from high potential value to very negative potential value through bulk soil, rhizosphere, root, then stem, and then leaves up to the air. And when we look closer to the system, we see that there are three big resistances or conductances for the transport of water: the rhizosphere, the soil root contact area, mucilage, root hairs, the root conductance, which depends mainly on its anatomy and root architecture, and then in the leaves, the stomatal conductance. And plants can control more or less these three resistances by exuding mucilage, by changing aquaporine activity, by growing, by developing its leaves. So plants have control on these conductances. And on this talk, we will focus on this middle conductance, the root conductance. So we want to improve plant tolerance to drought stress, but how to do it? So breeders have pointed out root traits which are associated with drought tolerance, like xylem diameter, so plants with lower xylem diameter spare water and are better in case of drought, suberization, aquaporine activity, hydrotropism. Yeah, I speak about hydrotropism actually. Growth direction, growth rate, hydropatterning, so initiating lateral roots where the water is, mucilage exudation, root hairs. So you see there are a lot of traits related with root architecture, root hydraulics that are linked to root water uptake. So here I listed them and I put in blue hydraulic traits and architectural traits in yellow. So just a few words about hydraulic traits. So when I speak about hydraulic, I mean not only conductivity, but also surface, so conductance. So for instance, root hairs, in my view, increases hydraulics because it increases the contact between the soil and the root. Ideotypes. So ideotypes is an old concept, 50 years old, and Donald defined it like a plant conceptual model which is expected to yield a greater quantity of grain, oil, or other useful product when developed as a cultivar. So the idea behind ideotypes is to have a conceptual view about combinations of root traits which would improve tolerance to drought stress, for instance. One very known ideotype is the deep, steep, and cheap ideotype of Jonathan Lynch. And here we will focus on ideotype for water mainly, so drought stress. And we will use maize plants as our model. So these ideotypes, or these optimal breeding schemes, focused a lot on increasing root depth. But for instance, if you read Bolaños in '93, he did 8 cycles of selection of tropical maize genotypes under dry condition, and he observed that after the 8th cycle, the root biomass and length were smaller in the high performance maize, meaning that root total architecture was not the main trait to ensure yield. So architecture is not the only trait to consider. In the second example, coming from Mathieu et al. In 2017, they compared, it was a modeling exercise, they compared a fast and slow growing genotype. And they had different soil depths. This is the x-axis. And in the y-axis, you see the difference in terms of yield between fast and slow growing genotype. And on average, if you take the average of all the simulations, whatever the soil, you have an average of 0. So having fast or slow genotypes doesn't change on average the yield. Of course, you see when the soil is a bit deeper, like here, 1.5 meter depth, you have a positive feedback of the high or fast growing genotype. But you still have a high variety between different scenarios. So it's not only the architecture, it's also the timing, how the root grows as a function of the scenario, the climatic scenario, the soil, and so on. Another counterexample coming from a DROPS project, it's a European project where more than 200 genotypes were sown all over Europe and compared in terms of yields. And here we picked up 2 genotypes, genotype 1 and 2, in 2 different locations, and you observe that the one who performs the best under a given environment performs worse in another one. That's known, everybody knows that, but it proves somehow that having ideotypes just based on rules, on the same rules, whatever the climatic scenario, doesn't make sense. So somehow the genotype ID has some limitations, and here I would like to somehow develop a bit this idea and try to find new conceptual framework to define ideotypes. So the 2 objectives of my talk are first to try to understand the role of combination of plant root traits for drought tolerance, and then to improve and develop the concept of ideotypes. And then also answer to this question, does root system architecture matter at the end? So what is an ideotype? You already defined it. But how can we build one ideotype? On the left-hand side, you have a conceptual design. This is typically deep, steep, and cheap. It's a conceptual ID. It's easy to use, easy to understand, but it's qualitative, so no value, no quantity, and it's static. So it gives you rules which are value whatever the scenario. On the other hand, you could go to explicit modeling. Explicit modeling means a 3D representation of a root system growing, perhaps with leaves and so on, with the exchange between soil, root, hormonal production, and so on. An explicit representation of the root soil architecture. Then you have more quantitative values, you have temporal evolution. However, this is very easy, very heavy to use, and it's also heavy to parameterize. And what we would like to try to find is quantitative ideotypes, which are at the same time easy to use, but quantitative and dynamic. So our methodology will be to build a conceptual model, simple, but which represents the impact of root traits on plant water uptake. And to do that, we have 4 challenges to tackle. First, we need to define root system properties, which makes sense. Second, we need to link these plant scale root properties to traits, to root traits. Third, we have to evaluate how the combination of root traits lead to different plant strategies to take up water. And fourth, we can define eco-ideotypes, which are function of the environment. That's these 4 challenges that we will try to demonstrate here. So first, a few words about explicit modeling. Explicit modeling is having a 3D root architecture, having plant parameters like time emergence of crown root, for instance, elongation rate per root type, KR distribution with root type and root age, and so on. You put everything in a 3D explicit model, which explicitly represents water flow, solute transport, nutrient uptake, and you predict water dynamics, transpiration, water flux dynamics. There is such a model called R-streams. I've been working on it a lot of time. I won't develop too much here. Just to tell you that with that model, we can model soil water flow, root water flow, the impact of macropores on the root growth, for instance, so the mechanical interaction between soil and roots, hormonal transport. So on the left-hand side, you see split root experiments that we modeled based on ABA transport in the xylem, or also the impact of rhizosphere. I won't develop that today, but just to tell you that we have this model. It will help us to have a kind of standard. We put all the state-of-the-art in this model, and we can always compare simplified models to that reference model. But that's not what we want to do here. What we want to do is to have a plant effective representation. And to do that, we first need to find these parameters and then make the link with between these parameters and root traits. So the questions are, how can we simplify a complex network like a root system? How can we represent this ability to extract water? And which traits influence those root system scale properties? To respond to these questions, we use the catenary hypothesis, meaning that plants are like electrical circuits where the water is transported through water flow gradients, and we work at steady state. And we use only first principles to try to simplify the system, mass conservation, Thevenin theorem, and we try to find these parameters. I won't go into details, but at the end, what we got are that two or three parameters actually, can represent a full root architecture. One of these is really easy to understand. This is a root system conductance. So we can define for any root system at a given time a conductance which represents the full complexity of the root system with the full hydraulic conductance distribution and the complexity in the architecture. We have a second set of parameters which are the root hydraulic property distribution that will be called SUF, SSF, or SUD in the rest of the talk. And then we have a conductivity which is called root compensation conductance, which is quite close to this one. And so we define these three equations. I won't go into details, I told you before, but just to show you that these equations are very simple. And with these simple equations, we can reproduce a very complex systems. And also that behind these equations, there are no other hypothesis than the fact that water is moving along the water potential gradient. Of course, these parameters are related to traits. They are related to root properties. For instance, here we run different simulations where we have different root radial conductivity changing with water potential. So here we wanted to represent how the soil dryness could affect radial root properties. And we had different scenarios. I won't go into details. For instance, one scenario where gaps were created between root and soil, one where we had aquaporine activation when the soil was drying out, other ones where we had combination of those. And you can see that as a function of local properties, like gaps, like aquaporine activation, you see different behavior in terms of actual transpiration, but also in terms of leaf potential. So now the next question is to link these two big parameters, root conductance and SUF, to local traits. How do we do that? And to which parameters are these global parameters, or to which root traits are these parameters linked to? Of course, if I would ask you the question, how the conductance of a root system depends on local root traits, you would probably tell me that it depends on radial conductivity distribution, on aquaporine activity, on xylem vessels, diameter, numbers, but also it depends on architectural parameters like the distance between lateral roots, the number of primary roots, and so on. On the other hand, we can also be interested not only into hydraulics, but also how the roots invade the soil. And in that case, the volume of the rooting zone depends also on local traits, like the growth rate, the lateral angles, the number of primary roots. So you can see that we can just conceptually make links between traits and plant scale parameters. And the challenge we had to face was to find an analytical solution to make the link between these guys and those guys, so the global variables. So to do that, what did we do? A bit of mathematics. So we developed analytical solutions of the water flow equations for root branches, and then we put all these root branches into conceptual implicit root systems and estimate planned scale parameters. So this was done by Félicien, actually he was sitting here, through two papers, a lot of equations. I won't go into details again, but just to tell you that now we have a tool where you give me traits like the angle, the radial conductivity, the axial conductivity, how these change with age, the radius of the roots, the growth rate of laterals, the growth rate of primary roots. You give me that, and I can give you the upscale properties. What is interesting is that you can also give me a change. So if you have you are a breeder, and you can have roots with a different distance between laterals. You tell me, okay, I have two genotypes, one with this average distance, one with that average distance. I can directly tell you, if you increase this distance by 20%, the conductance of your root system will be that amount different. So you see, we are going further, or we are getting closer. Sorry, we are getting closer to a quantitative characterization of the root system. So, does the root system architecture matter? So here, what we do is an exercise. We took architectural parameters from a Lynch paper. We took hydraulic parameters from a review of the literature, where we have a lot of maze measurements, radial conductivity, xylem conductance, and so on. And what we did is to analyze this genotypic domain, or this trait domain. So we run combinations, all possible combinations of all the traits in the ranges which were found in literature. And we generated 10,000 potential root system architecture. And we did it with an architectural model, so an explicit 3D model. So we had 10,000 simulations of root architecture, but not only root architecture, but root architecture with hydraulic properties. So the dependency of radial and xylem conductivity with root types and root age. So we had 10,000 root systems, root system architecture, root hydraulic systems actually. This is our reference. And then we used the model of Félicien to represent, based on these traits, the upscale parameters, the volume of root, the conductance of the system, and so on. And we compared both. And the question was, do we need the explicit representation of the 3D architecture to be able to represent root conductance? Here what you see is actually the results. So you have the model relative difference between the simplified model and the architectural model for the root conductivity, for the average depth of the rooting system, and the volume of the root system. And what you have in the x-axis is actually a coefficient of variation that we put in the architectural model. So the architectural model didn't only run the review parameter, or the list of parameters that we found from the literature review, but we added to these values, to these reference values, some variation. The idea is that the more variation you have, the more variance you have in the parameters, the more noise you will have. So we can have a lot of different architectures which all have the same average value. I'm not sure I'm very clear here, but the question is, can we compare root architecture or representation of similar root architecture together with the simplified model? Well, the answer is that on average, the error that we are making is really small. So we are below 5%. So this blue line is the average error for KRS, and this is the average error for the average depth, the median depth. And also you see that for the root system volume, we are also very good. So what it means is that if you provide us only root traits without the architecture, but just average root traits, average distance between laterals, average number of primary roots, average value for KR, KX, and so on, we can predict you the conductance of the system. Okay, this was only modeling compared with modeling, so I know that it's highly criticizable. But here what we did is compare the values that we got of the root system conductivity together with literature review. So each boxes here represent values of the system conductance found in literature. And this big gray envelope represent the phenotypic domain. So when you combine all the sets of parameters, if you put them in the simplified model, that's the actual envelope you get. And you see, and this is age of the root system. And you see that we are, on average, of course, on this, at least comparable with the data that you can find in the literature. Of course, this is much bigger, that the uncertainty is much bigger than what is found in literature, because what we did is actually exploring the full possibility of combinations. Some of these combinations cannot actually exist, okay? And that's why we are much wider, but on average, you can see that the average or median line is following more or less where these studies have found the root system conductivity. So we can somehow estimate root conductances based on local traits, but also root invasion volume or average root depth. So let's go to the third challenge, plant strategies. So how can we define plant strategies? So here we decided to define plant strategies as a combination of these macroscopic parameters. So remember, we have two parameters, the root conductance, the root system conductance, and also the average depth of the root system. And here I made this table with two entries, shallow root system, extensive root system, low root conductance, high root conductance. This is only the two parameters. And you can think about these combinations, like, for instance, a low root conductance and a shallow root system. This will be a system very conservative, not transpiring a lot, small root systems, closing the stomata probably very early. So this is very conservative. On the opposite, when you have high root conductance and an extensive root system, this is a plant growing very fast with a very high conductance, which transpires a lot. I called it an aggressive plant. I didn't know that plant could be aggressive, but yes, that's an aggressive behavior, let's say. You also have conservative behavior for plants who have an extensive root systems, so they are growing fast, but they don't transpire too much. They close early the stomata, and they don't have a high conductance. And at the end, you have a risky kind of behavior where you have shallow root system, but very high conductance, meaning you don't have a lot of roots, but you transpire a lot. So it's quite risky. So one of the conclusions of this table is that there is no one ideal conductance. You cannot say, oh, I want my plant to have the biggest conductance as possible. It makes no sense. Actually, we should think in terms of strategies. None of these strategies is bad. It depends on the environment where these plants will grow. And so the idea is to take a bit of distance with ideotypes and rather speak about strategies and see how strategies fit or not to a given environment. So there is no one ideal combination of macroscopic root system parameters, but there are different strategies. When we speak about strategies, we also need to speak about time. So here what you have is our 9 simulations, actually, picked up among 10,000 combinations of simulation, or 10,000 simulations. So each color represents a different genotype with a set of root parameters. And you see how it behaves in time. So they all start from 0, so the top of the soil, and they grow down. This is the depth. This is the conductance. And you see really different strategies. For instance, this red guy here is growing slow, not going very deep, but he has a very high conductance at the end. On the other hand, you have this blue guy here, which grows fast, deep, but with a low conductance, which is very, very conservative. Okay? And then we can try to make the link between combinations of root traits and plant strategies. So these are, each point there is one of these 10,000 simulations. And we put together simulations that we found close to each other. I mean, we try to aggregate simulations into groups. And we aggregate them in terms of average depth, convex hull volume. This is the volume of the total routing system. Well, this is actually the volume which links the extremes of all the root system. The total volume of the root system, and then conductance. And you see appearing different strategies. So you have these blue guys which have high KRS but relatively average ZUF, and you have this green guy with rather not deep, rather shallow but low conductance. And this is just the combination of root traits. We can make the link between these strategies and between these strategies and the table. For instance, the green guy is very conservative, the red is conservative, this blue here is risky, and the other blue, I don't know if you can discriminate the two blues, the two blue shapes are risky and aggressive. So now we are able to make the link between a set of local root traits and plant strategies. Now let's speak about eco-ideotypes. So what is the idea behind eco-ideotypes? Is that the efficient strategy might differ as a function of the environment. So what we did here is to go back with the data set we had from the DROPS project. So we have different fields throughout Europe where we have the climatic data, we also have the soil characterization, and we try to see how the different genotypes that we can create now with combinations of traits, how these different genotypes or virtual genotypes develop between these environments. So we have the genotype parameters from experiments, we have the characterization of the climate, of the environment, and we model the root system or the maize plant from sowing to flowering, because flowering is a very, very delicate period where water stress will affect a lot the final yield. And basically what you have here, I show you the results only for two sites, a site one here and another one there, which have very different environments, very different climates, sorry. And we see how the change, the cumulative transpiration is a function of traits. So what you have there are traits. So for instance, you have radial conductance of certain types of roots, you have the distance between certain types of roots, you have the average angle, and so on. And what we checked is how these genotypes were performing as a function of, no, the opposite, how the different traits affected the performances of the genotype. We were trying actually to relate performance of a genotype, of a virtual genotype, to certain traits, which are the important traits to consider under a certain environment. And what you can see, these are the green traits, is that the important parameters, the important root traits, which will give to plants resistance to drought stress, they differ as a function of environment. So here, for instance, you see that you have distance between laterals, you have radial conductance, and here you have velocity or other things. Okay, so to conclude, I try to prove that there exist plant scale parameters that can be derived from biophysical laws which fully characterize the root ability to extract water. These parameters are hydraulic parameters, but also volumetric or geometric parameters. We have developed a new model which makes the direct link between a set of root traits and root system properties. And we can answer questions like, how much does my root conductance change if I had 20% longer lateral roots, for instance? Then we can define plant strategies, which are considered as a combination of root system properties. And we can define 4 types of strategies. And then we can also combine these tools together with soil and climate models and show how or define optimal plants. And we call these optimal plants or these optimal combinations of traits eco-ideotypes. Eco because they depend on the environment. Final question was, does root system architecture matter in the quest of motor and plants to water stress? I would say that root traits matter, but more than the actual root distribution or the root system architecture. So we don't need anymore the root system architecture. We just need the average traits if we want to develop drought tolerance plants. And root traits matter, but not only. You need to combine them with a very fine definition of your root hydraulic traits. So not only average radial conductivity, but conductivity depending on root age, root type, and so on. So of course, this presentation was based on a lot of assumptions. There are a lot of other things that we need to deal with, like the rhizosphere. How will the rhizosphere affect these findings? The plasticity. So we didn't explicitly consider plasticity right now. So there was no direct effect of the environment on the root system architecture. We know it exists. We have ideas to deal with it, but it was not yet implemented. And another thing that we need to work on, and we're actually working on this, is how we can link these root segment properties to anatomy and to aquaporine activity. And for this, we are building, or I should say, Valentin Couvreur and Xavier Drey are building a model, an explicit model of the root cross-section, where they can change a lot of parameters like permeability of the membrane, plasmodesmata density, shape of the cells, permeability of the membranes, and they can see how changes in local properties at the root cross-section affect effective radial conductivity. Okay, thank you for your attention.
We have time for a few questions. Please use the microphone.